So electric potential is the work done per unit positive test charge to move it from infinity to a point in the electric field. So work done per unit positive test charge to move it from infinity to a point in the electric field is called electric potential. Electric potential V is work divided by test charge, work in joule, charge in coulomb. So joule per coulomb is volt. Work scalar, charge scalar, electric potential, also scalar and measured in volt. Now, electric potential is equal to work is F into D divided by Q. So V is equal to E times D because electric field strength is F divided by Q. Now from this, we can write electric field strength V divided by D. We have done this in A1 and AS. E is equal to V by D. But this shape of the formula is acceptable in paper 1 and in paper 2, not in paper 4. For the paper 4, we will write it minus delta V over delta D. So this expression, this formula will be used in P4. Look, reason behind, more details are required. So when work is done on the charge, distance must be covered. So distance of the charge from the fixed point must be altered. So that's why it's delta D. Without changing distance from the fixed point, no work is done. So we have to mention change in distance from the fixed point. And the distance is only covered, work is only done when there's a potential difference. If two charges are at the same potential, no work is done. That's why we have to write the potential difference and this negative sign with the passage of time. As the work done on the charge, the potential difference decreases. Like when the water flows from higher level to the lower level, the level difference decreases. So that's why this negative is showing the decrease in the potential difference as the work done. So we have to write E is equal to minus delta V over delta D. So if the question is, what is the relation between E and V, electric field strength and electric potential? So we will write electric field strength E is the negative potential gradient of potential against distance graph. Mean, if the graph is plotted between electric potential and the distance, then the negative gradient of that graph will be electric field strength. So E is equal to minus delta V over delta D. Electric potential is scalar, distance scalar, but electric field strength is a vector. Electric field strength is measured in Newton per coulomb or volt per meter. So it has two SI base units. Now move to the next. Again, electric potential V is equal to F times D divided by Q. Now this force is definitely the electrostatic force, and this charge is the test charge, and this distance is covered by the test charge. So we can write V is equal to electric force from the Coulomb's law 1 over 4 pi epsilon naught Q1 Q2 over D square times D divided by this test charge Q. Now, one of the charge which is considered test is cancelled, one distance cancelled, so we are left with electric potential is equal to 1 over 4 pi epsilon naught Q divided by D. So definitely this remaining charge is the point charge in nature. So this is the formula for the electric potential. Now, this is a neutral sphere. It has no net charge. Neutral. But when a charged rod, suppose rod is negatively charged, is brought close to this neutral sphere, then electrons from this side will be repelled. Surface electron will experience repulsive force and they will be transferred to the other side of the sphere. So all electrons will travel at the surface. No charge will travel through the sphere because thus free electrons are present only at the surface. So each electron has same charge, same distance covered from one end to the other end. So same force experience, same work done, same charge. That's why when electrons are shifted from one side to the other side, this electric potential, which is Fd divided by Q, charge of each electron constant, distance covered in all direction from one end to the other end through surfaces same, force experience same. So the potential electric from one end to the other end will be same. So when it becomes charge after electrostatic induction, if it is solid, then the charges will appear beneath the surface. This is a perfect sphere. So the charges will appear beneath the surface, whether you are charging it positive or negative, right? But the potential at this perfect sphere will be same from one end to the other end. This same, this surface the same, this same, similarly this end to this end same, this end to this end same. So the potential is equal at all points of the surfaces because same force experienced, same distance covered, same charge. So the potential from one end to the other end throughout the sphere surface is same. Now, when we will plot the graph between electric potential and the distance, so this is the right side surface, this is left side surface. At the surface, potential is maximum. Here at the surface is maximum, but it remains same constant maximum throughout the surface of the sphere. And then away from the surface, according to this formula, V is equal to 1 over 4 pi epsilon naught Q over D. D and V both are inversely. So inverse relation. So this is the graph for the V and D. So D in meter and this V in volt. This is electric field. This is electric potential graph for positive charge, right? Now, potential is scalar, but remember, due to positive charge, it will be considered positive. Due to the negative charge, it will be considered negative. but it will remain scalar. Now here, the gradient of this graph, look, E is equal to V divided by D in A1 AS, but in A level delta V over delta D. So the gradient of this graph is electric field strength. So look, from this end to this end, the gradient is 0. That's why the electric field strength inside the sphere from surface to the surface remains 0. We have done. And then look, the gradient is gradually decreasing. So away from the surface of the charged sphere, electric field strength decreases. So the gradient of this graph will be electric field strength. Suppose we draw again the electric field graph, electric field strength graph against D. This is electric field strength, this is D, this is radius, this is radius. Between two radii, electric field strength is 0. At the surface, it's maximum. At the surface, it's maximum, and then gradually decreases. So look at the two graphs. Here, from this R to R, the gradient is 0. That's why from R to R, electric field strength is 0. And next, according to this formula, this one, E is equal to V by D. So E times D is equal to V, mean the area of this graph, area under the graph of ED, this is electric potential. So the gradient of potential distance graph is E, and the area of ED is electric potential. So these are the two graphs for the isolated charged sphere, one graph for VD and other graph for the ED. Now suppose we have two charges, one is positive, other is negative. This is the pattern of the electric field. Okay, now here at the surface, this field is maximum towards right. Here at the surface, field is maximum towards right, and this is the area where the field is weak. So when we will draw the electric field strength and the distance graph, at the surface, electric field maximum inside 0, inside here 0, at the surface is maximum and positive because the direction is right, and this is the weak field, not 0. So we will join these 3 points. So this is the ED graph as we have done in the previous lecture. But now we have to draw VD graph. Look, this is the radius of the positive charge. This is the radius of the negative charge. At the surface, electric potential is maximum. For the positive charge, it is positive maximum. For the negative charge, it is negative side maximum. So when both potentials, positive, negative, are added, definitely there will be a 0 potential. So away from the surface decreases, away from the surface decreases, but sometime rests at some point it will be 0. And then from surface to surface, it remains constant. So this is constant. So this is the V and D graph when one charge is positive and other charge is negative. This side for the positive charge, okay, so this is 0. So inversely proportional. surface constant, surface constant. And this is the VD graph between positive and the negative. This is ED graph. This is VD graph. Okay, now suppose we have two similar charges. Both are positive, and according to our previous knowledge, this is repulsive electric field. And this is the neutral point where no electric field. Now, when we will draw the graph between E and D, as we have done earlier, so E at the y-axis, D here, this is the radius of the first positive. So the field at the surface is maximum. It is headed towards right, so it's maximum positive, but inside zero. And this is the radius of the other positive, right side positive. Its field is maximum, but directed toward the left. So the maximum in the negative direction. And this is the point where no field. So the graph will be like this. So this is the ED graph when both charges are similar. Now for the potential against distance graph, so potential is scalar. It's positive for the positive charge, negative for the negative charge. At the surface, it is maximum positive due to the positive charge. And from one surface, it does remain same. And this is the radius of the other positive charge. So yes, it's positive and the maximum. So it remains maximum from surface to surface. So when both are positive side, so no chance of the zero potential, but due to the smaller value, it can be reduced to the minimum value. So this is the graph for two positive charge sphere when both are positive. So look at the graph. When two charges are positive, this is the shape of the ED, and this is the shape of VD. We have to remember. And definitely when both charges will be negative, then this line will be here, this line will be here, and the graph will be like this. So this is for the positive and this is for the negative. And similarly, then this will be in the opposite direction. Suppose this one, just a reflection for the both negative. The same shape. Okay, now suppose we again write V is equal to work done per unit charge. So the work can be written as charge multiplied by voltage. And this work is the energy. So which energy? It is electric potential energy. This is charge multiplied by voltage. But do remember, this is the test charge, and this potential must be from the point charge. So one is the test charge and other the potential from the point charge. So electric potential energy is, suppose Q1 multiplied by potential 1 over 4 pi epsilon naught Q2 divided by D. This is representing the test charge. This is representing the point charge. So electric potential energy formula will be 1 over 4 pi epsilon naught Q1 Q2 over D. So electric potential energy is equal to 1 over 4 pi epsilon naught Q1 Q2 over D. This is the formula for the energy, electric potential energy. Now look, number one formula we did electric force 1 over 4 pi epsilon naught Q1 Q2 over d square. And number 2, electric potential energy 1 over 4 pi epsilon naught Q1, Q2 over just D. This is D square, this is D, this is the difference. So it becomes the energy, electric potential energy. And number 3, electric field strength 1 over 4 pi epsilon naught Q divided by D square. And this Q is the point. And the number 4, electric potential is equal to 1 over 4 pi epsilon naught, then Q divided by D. So D square and Q single for the electric field strength. This is electric potential energy. This is electric field strength. And when single Q, single D, then it says electric potential. Okay, now energy, electric potential energy, E PE is equal to 1 over 4 pi epsilon naught Q1 Q2 over D. If the charges are same Q1 Q2, then we can write Q. Then this electric potential energy will be equal to 1 over 4 pi epsilon naught Q square over D if both charges are equal. Next, suppose this is the fixed charge and this is another similar charge and it is brought close to this. So due to repulsion between the similar charges, work must be done on the moving charge. So to overcome the repulsion, yes, when the charges similar are getting close to each other, work must be done on the moving charge. Thus, work done to overcome the repulsion is converted into energy. So which energy of the charge is? Electric potential energy. So the statement final is, when two similar charges are brought close to each other, when two similar charges are brought close to each other, work done against their repulsion is stored as electric potential energy or electric energy. Hence, electric potential energy increases. So whenever we will bring two similar charges close to each other, their electric potential energy increases. And the formula for the electric potential energy is this: if two charges are similar, then Q square over D. But when they are released, when similar charges are released, whole of the electric potential energy is converted into kinetic energy. So if the charges are same, then 1 over 4 pi epsilon naught Q square over D is converted half mv square for first, half mv square for the second, because they are equal in charge, equal in mass. So we can write then 1 over 4 pi epsilon naught Q square over D formula will be half mv square, half it becomes mv square. But if they are different in charges, different in masses, then the electric potential energy 1 over 4 pi epsilon naught Q1 Q2 over D will be equal to 1 over 2 M1 V1 square 1 by 2 M2 V2 square. So it depends on, yes, the nature of the charges, equal in charge, equal in mass, okay? And similarly, when two negative charges are brought close to each other, again, work is done against repulsion. So electric potential energy increases. So the conclusion is when similar charges are brought close to each other, work done is converted into electric potential energy, hence total energy stored by them increases. When released, it is converted into their kinetic energy. Now, positive charges. Here positive charge and here negative charge. No work is done. Due to attraction, they are getting close to each other, so their kinetic energy is increasing because due to attraction they are accelerating, their speed is increasing. So when two charges, opposite charges, are attracted towards each other due to acceleration, right, their kinetic energy increases, and on collision, whole of this kinetic energy is converted into light and heat, which is the loss of the energy, and there will be spark. But when work is done against their attraction, so when the opposite charges are moved away from each other, but within the electric field, then work is stored as electric potential energy. So when two similar charges are brought close to each other, potential energy increases. When opposite charges are, yes, moved away from each other, then electric potential increases because we have to do some work against their attraction. So when released, when two opposite charges are released, then their electric potential energy again converted into kinetic energy. Now suppose one object is charged and other is neutral. So this is charge Q1, this is charge Q0. So according to the formula, electric potential energy 1 over 4 pi epsilon naught Q1 Q2 over D, one of the charge 0. So there is no increase in the potential energy, whether neutral is brought close or far from each other, right? From the positive charge, no change in the potential energy. So when positive, similar, negative, similar charges are brought close to each other, potential energy increases. When positive, negative are coming close to each other, kinetic increases. When they are moved away from each other, potential increases. But when the neutral is getting close or moving away from the charge object, no change in the potential energy because one of the charge is 0, so E becomes 0. So no increase in the potential energy. Suppose this is a charged sphere and this string is insulated. It is positively charged. Its field is like this. Now, a neutral object is brought close to this hanging charged affair. Suppose this is the box of metal. Due to positive polarity, there will be charge distribution on the box inside. Negative charge will appear, and the outside positive charge will appear. Number of the positive, number of the negative charge will remain same, and the pattern of the field will be like this. Positive to negative. Okay, when this metal is connected with the earth, then the outer positive charges will disappear. So this is the appearance of the charges. Inside positive and outside positive charge is neutralized due to the earth. Now, when the charge sphere is isolated, electric potential at its surface can be calculated 1/4 pi epsilon naught Q divided by R. This is the formula for the electric potential for the isolated charge sphere. Electric potential at the surface for the isolated, not resultant. For the resultant, for the two charges, positive charges, we have to add one positive, one negative, we have to subtract because it's scalar. Now here, when the neutral object is brought close to each other, there is no change in the electric potential energy. It remains same as carried by the individual charge sphere. But same energy is shared among the more number of the charges now. Initially, suppose here, 10 charges were sharing this energy. Now, 10 these charges, suppose 5, 7 these charges. So the same amount of the energy is shared among the more number of the charges. So look, electric potential is work done per unit charge, mean energy divided by charge. So in this situation, charges increases, but the no increase in the energy. Hence, the potential in this case will decrease. If the electric potential for the isolated is coming to 40 volt, when a neutral object is brought close to each other, is placed inside electric field, definitely the electric potential will drop. It will be maybe 120 volt, 100 volt, 80 volt. It depends. So remember, this formula for the electric potential is for the isolated charge, but when neutral object is brought close to it, there is no change in the potential energy. It remains same, but the number of charges sharing that energy increases. Hence, the potential decreases.